So I'm waiting for all of us to join. So let's just wait a few more minutes and let us wait for everybody to join. So you would need to have your question paper with you. I don't know how you want to manage that if you don't have like multiple devices. Yeah. So for those of us that are here already, um, so this revision class, basically I'm going to be solving those problems that I sent to the channel. So they are 170 in number. So this class, this is not only going to be our class, this is not going to be the only class we'll be having. We'll be having subsequent classes as well until we have exhausted all the 170 questions. So I will be, most likely I would prefer that we are able to solve at least, let's say, 20 to 30 questions per class, so that we can cover on time before the exam starts. So I'm still waiting for few persons to join. We are only 6 here. We should be more than 6. Please, if you can go on WhatsApp now, tell your colleagues to please join ASAP. I don't want them to miss anything, because once I start, then it's I won't be able to go back to anything. Okay, we have 8 of us here now. Okay, I think we have 11 persons here, so I'm going to start like that. So I want all of us to have our question paper with us, and please always send feedback in the chat so that we know if we are all following. So for question number one, so this question number one is about semiconductors. Now, quickly, this might take time, but I'll try not to let it take too much time. So I'll be talking about okay, not all of them are active. So quickly, when I want to answer a question, I will briefly, talk about, what the concept is about and all of that. Now, this particular question is saying in a common, okay, I think we are 22 now. So we have question 1, so I'm taking question 1 now. In Roman figure 1, we have in a common collector amplifier circuit, what is the input signal? Like, the input signal is applied between the emitter and the collector, and then a PN junction diode conduct current when is in reverse bias. And then Roman figure 3 says that if a reverse bias voltage is applied to a PN junction, depletion layer width is increased. So quickly, before I even answer the question, let me talk about semiconductors quickly. You see, semiconductors are those guys that have their conductivity between a pure conductor and an insulator. So which means that they don't really conduct very well, but at the same time they can still conduct a little. Now, here's one jam question that you need to take note. Effect of temperature on semiconductor is that for the semiconductors, when you increase their temperature, their resistance, it will decrease. Please be taking note please be taking note of all this thing I'm saying. Please, I won't be able to start over. That is why the time has been set. You would probably get access to the video later, I think so. So please make sure you are taking note of everything I'm going to be saying now. So you need your pen and paper. Now, so what I'm saying is that effect of temperature of semiconductor is that when you increase the temperature, the resistance actually decreases, which causes their conductivity to increase. Their conductivity will increase. So, but unlike pure conductors, for pure conductors, the higher the temperature, the higher the resistance, hence reducing their conductivity. So that's one major difference between a pure conductor and a semiconductor. By the way, if you're on my TikTok page, you can check a summary video on semiconductors. You'll see it in one of my videos. So I made a full detailed video there. So let me go to this particular question. Now, one of the application of semiconductor is that we have what we call, first of all, we have what we call a junction diode. The junction diode looks like this. The junction diode looks like this. So let me quickly show us that. So this is what the junction diode looks like. It has a partition in between, and this partition, so this is the partition. Now from this place, now we have a P and we have N. So in this junction diode, we have a P type and we have the N type. The two of them are fused together. Now we now make a transistor by actually joining two of these junction diodes together. So imagine I'm joining two of these junction diodes together now. So that would give me something of this nature. I will have this. So let me draw that. Then I will have this, and this. Please just pay attention to what I'm doing now. So you can have it in two ways. So is that sometimes you have a PNP transistor or you have NPN transistor. Now these two guys are transistors. Don't forget, this is a junction diode, and these two are transistors. So you can check that my video out. I made everything in detail. So what happened is that these two places, these two ends, they always serve as the emitter or emitter, and this serves as the collector. So this one will be the base. The same thing also works in this place as well. So this emitter, collector, and then the middle guy serve as the base. So another way you can see this drawn is that you can see this drawn in a circular manner. I'm sure if you have solved your past question very well, you would have seen something similar to this. So here you have the base, then you have the emitter, and you have the collector. So in this place you have arrow in, and then in this place you have this. This is just showing that this is our base. Now this base, this emitter, let me call this E, let me call this no, that's not the emitter, this is the collector, this is the emitter, and this guy is our base. So basically what the question is saying is that in common collector amplifier circuit, the input signal is lying in between the emitter and the collector. That is not true. That is not true, in the sense that the input always is not, the base is not doing anything. The base is just being there to neutralize the effect of the collector and the emitter. So that particular Roman figure 1 statement is not true. So it's not true that the input signal is applied between the emitter and the collector. No, this is where the input signal is always applied. The input signal is always applied through the collector. Please take note of that. So that is that. I don't want to go into too much, because if I want to go into too much details, even these semiconductors alone, I will need to take the rest of the evening to explain it. But just take note of that. Now let me now quickly explain Roman figure 2. So this one is more easier for you to understand. Now there's something called depletion region. Using that junction diode that I drew earlier, so let us assume that we have a P type semiconductor and we have N type semiconductor. Please, when we are done with this class, go to my YouTube and check out that video on semiconductor. Some of the things that I'm saying here you might not really understand very well, because you don't know well about semiconductors. So but I will just be explaining based on the questions only. So this is saying that a PN junction diode conducts current when it is in reverse bias. Now what is reverse bias and what is forward bias? So I'm going to show you two things now. So if we have a circuit in this place, if I create a circuit, now let me create another junction diode, then I create a circuit around this as well. I create a circuit, so let this be this, then we have this. Now what is forward bias and what is, yes, I think you still have access to the video. YouTube allows us to like save the video. So now please let's continue. Now forward bias, is when you have a p-type semiconductor, an n-type semiconductor, n-type semiconductor, and a p-type semiconductor. So don't forget what I said already. A junction diode is always the mixing together of a p-type and n-type semiconductor. So those are the two types of semiconductors. We have p-type, n-type. In my video you will learn about what a p-type is and what an n-type is. So when you bring them together, that is when you form a junction. So this junction, actually in between this place where the red line is where we call the depletion layer. It is where we call the depletion layer. So what usually happen is that in the forward bias, this is the forward bias and this is the reverse bias. Now why is this one the forward bias, why is this one the reverse bias? The idea is that if you look at the p-type for semiconductor is like the positive terminal, and the n-type for semiconductor is like the negative terminal. Now in your battery, you know that the longer side is always the positive one and the shorter side is the negative one. So whenever a positive terminal of a battery is connected to the p-type semiconductor and the negative terminal is connected to the n-type semiconductor, then the kind of connection you have there is a forward biased connection. But if you reverse the case such that the n-type semiconductor is connected to the positive terminal of the battery and the negative terminal is connected to the positive terminal of the battery, that is where you have a reverse bias connection. Now in this reverse bias connection, this is what usually happens. So please let me know if you got the explanation of the forward bias and reverse bias. So I would always need your feedback so that I know how to proceed. So did you get that explanation of the forward bias and reverse bias? I'm asking if you understand the explanation of the forward. Okay, for those that did not get it, I'll just brush through it again. For a junction diode, you have a p-type, you have n-type semiconductor. Now the positive terminal of the battery connected to the p side is the forward bias. I mean positive to p-type, negative to n-type, forward bias. When you reverse it such that the positive is connected to the n-type and the negative is connected to the p-type, that is the reverse bias. Now what is now the depletion region? You will notice that in the first place when I drew this thing, I did not put any space in between them. So intentionally I put a space here because of the purpose of explanation, to explain what we call the depletion layer. So actually in that junction, the junction in between these two, there is a depletion layer. And then what do you think will happen as current is flowing in this place? So imagine current wants to flow here now. So current is going. As the current is going in this place, let's say it enters this p, you can notice that if this space is too wide, then current will not be able to make it properly into this place so that they can continue the movement. So now let's now see what is the effect of this forward bias and reverse bias. You see, in forward bias, from what we know already, we know that like poles repel, or like charges repel, while unlike charges they will what? Attract each other. So like charges repel, while unlike charges they will what? Repel each other. So let's now see the implication of that here. So this is a positive kind of guy, and this is also the positive terminal. What will happen to the two of them? They will repel, in the sense that they cannot come closer so that they are on the same side. You can't say that this p now is going to be attracted to this guy. If it's going to be attracted, what will happen? That means that this positive terminal will kind of like pull this thing onto itself. It will pull it as if it's moving it like with a string to itself. That will be attraction. But because they are both positive, what will happen? It will push it away. So what will happen when it pushes it away? This thing will be getting closer to n. When you look at the other side too, you notice that this is a negative terminal, another negative terminal here, negative. So this one too will be pushing. So there is pushing from the right and there is pushing from the left. So what will happen to the space in between them? The space will close up, and then current will now be able to what? Will be able to flow better. That is why in a forward bias, there is increase in the flow of current and resistance will be reduced. But when you go and look at this reverse bias, the positive terminal is here and this is the negative terminal for the semiconductor. This is the positive terminal and this is the negative terminal. So what you notice will happen is that this positive will want to attract the negative to itself. So therefore what is happening is moving it away, and then this negative also wants to attract the positive terminal, so it's also moving it away. What will happen to this space? This space will become wide, and then resistance will now increase and the current will now decrease. So that means that in a reverse bias, current is not always increasing, it is always decreasing, while in a forward bias there is more current that is flowing. So if you look at that question now, a p-n junction diode conducts current when reverse bias. So is that statement true? So I want you all to answer. Is that statement Roman figure 2 true, saying that a p-n junction diode conducts current when reverse bias? When reverse bias, is that statement true? Please, I will always be counting on your feedback so that I will know that. Very good. Okay, very good. MSD said no. Yeah, that's correct actually. So no, they do not. Yeah, very good. So that means that Roman figure 1 was not true. Roman figure 2 is not true. Now let's now look at Roman figure 3 now. I think without me saying anything, you can answer whether Roman figure 3 is true or not. So now we are done with Roman figure 2. Let's go to Roman figure 3 now. Roman figure 3 says that if a reverse bias voltage is applied across a p-n junction, what will happen to the depletion layer width? With the depletion layer, will it increase or will it decrease? So what is that true? Roman figure 3, is it true? Roman figure 3, is it true? Roman figure 3, is it true? This one is talking about the depletion layer width. What will happen to it in a reverse bias connection? What will happen to it in a reverse bias connection? So is that Roman figure? Yes, true. Please, you should be with your printout because the question is already there. Yeah, so very good. So you all got it. So that means that Roman figure 1 and 2, they are false. Only Roman figure 3 is what is correct. Very good. I like the fact that you all are following me. Now let's go to question number 2 like that. So that means that the correct answer for that number 1 is D, because the question says that which of the above is or are wrong. Which of the above is or are wrong. So the correct answer is D. Roman figure 1 and 2 they are the ones that is wrong. Roman figure 3 is correct. So now let's go to number 2 now. Number 2 question says silicon doped with aluminum and germanium doped with arsenic become. So before I answer the question, let me quickly introduce you to the concept of doping. So don't forget to check that video out on TikTok. Actually, I've made a lot of things there. Now, what is doping? You see, semiconductor naturally, they do not conduct, they do not conduct electricity. They do not conduct electricity in the sense that they are always they are always in the sense that they have so let me give you an example now. So in this outermost shell now, semiconductors, we have 4 electrons in their outermost shell, and from what we know about valency and everything, you will, to complete your octet structure, if you have 4 in your valence, that means that to complete octet structure is either you lose the 4 or you gain 4. Now since you have both it will not be convenient for me showing the question here. That is why I said everybody should have downloaded the question from the Telegram channel, and I think some people sent it on the group page as well. So please let us work together so that everything will be effective. There's no time. You can see we've used like 51 minutes already, and we are still on question number 2. That's very, very slow, but so I'll be a little bit faster so that we can finish all the questions here. So now, so what happened is that before this guy can conduct electricity, they need to go through the process of doping. So what do we dope with? We dope with 2 things. We dope with, number 1, a pentavalent. We dope with pentavalent elements, and we dope with trivalent elements. So what is this doping really? Doping is simply the addition of impurities to semiconductors. Addition of impurities to semiconductors. So when you add impurities to semiconductor, you produce two types. Is either you produce a p type. This p type, it is like the positive guy, or you produce n type semiconductor, is like the negative one. So how do you now produce what's it called? If you dope with a pentavalent element, you always produce what we call n type. You produce n type of semiconductor, and then when you dope with trivalent, you produce p type. So you want to take note of this as well. Jam can ask you that question. Pentavalent, you produce n type. Trivalent, you produce p type. Trivalent, you produce p type. So take note of that. Now let's now go and answer the question that is being asked. Silicon is actually a semiconductor. Silicon is a semiconductor. So they now doped it with aluminum. So what do you know about aluminum? You know that aluminum is Al3 plus in the ionic state. That means that aluminum has how many electrons in its valence shell? That is trivalent. Aluminum is trivalent. So when you use aluminum to dope silicon, what kind of semiconductor will you get? N type or p type? So let me know your answer. What will you get? N type or p type? When you use aluminum to dope, aluminum is trivalent. So what will you get? Very good, p-type semiconductor. So now, with that now, you know you can delete option A and C sef. You can delete option A and C. Very good. So now, the next one is germanium. So who know? Do you know the group that germanium belongs to? Germanium. Which group does germanium belongs to? Which group does it belong to? Germanium. Which group does it belong to? Very good. Group 5. So that means that it is what? Pentavalent. So that means that germanium is what? Pentavalent. So that means that when you dope with germanium now, you now produce what? N type. So the correct option there will be option D, p type and n type semiconductors respectively. So the first one was p type, the second one is what? N type. So that is basically what that question is asking you. So get that correctly. Okay, let's move to question 3 now. Let's move to question 3 because there is no time. We are spending so much time already. I was thinking we only use like okay, question 3. Question 3, I think I've mislabeled that. Question 3. So we have a material of mass 1 times 10 raised to the power 5 kg. So the mass of the material is 1 times 10 raised to the power 5 kg. That's the mass of the material. Undergoes a fission process. Fission is the breaking. Fusion is the coming together of smaller ones to become bigger ones, while fission is the breaking down of bigger ones to become smaller ones. That's fission. So when it undergoes this process, what happens to it? It reduces its mass to 99.8%. Calculate the amount of energy released in the process. So when you see questions like this, it reduces it to what? To 98%. So reducing it to 98% implies this. Come in. Are we still together, everybody? Okay, very good. So let me continue. Now, this question says that so original mass is this, and then it undergoes a fission process which reduces its mass to 99.8%. So the mass was now reduced to 99.8% of M. Now, the question wants us to find the amount of energy that was released. What will be responsible for the energy that will be released will be the mass that was lost. So you can see that this thing has not really lost that much mass. So the full mass is like 100%. So the new mass now is at what? 99.8%. So we can just calculate percentage loss. So percentage loss will be 100% minus 99.8%. That's around 0.2%. So that will be 100 minus 99.8. Yeah, that's 0.2%. So now we will now go and find how much of this mass is 0.2%. So 0.2 over 100 times 1 times 10 raised to power 5. So that would then be, so that should be, this 0 will reduce this to 3, and then we can use one of these to reduce this. So at the end of the day, we have what? 200 kilogram. So that means that the mass that is left is, the mass that was released rather, is 200 kilogram. Another way you can also do this is that you can find 99.8% of this mass, then subtract the result together, then you'll be able to find the mass that was lost in the process. So once you find that mass, then what you will use here is what we call Einstein's energy equation. Einstein's energy equation. And what is that? E equals mc squared. E equals mc squared. So in this case, the mass that was lost is 200 times the speed of light is c. C is the speed of light, which will be 3 times 10 raised to power 8 or raised to power 2. So that will be 200 times what? 9 times 10 raised to power 16. And if we do this very well, 2 times 9 is 18. 18 times 10 raised to power. This is double zeros, so that will be increasing this one by 18 as well. If we want to write the answer in standard form, that will be 1.8 times 10 raised to power 19 joules. I believe this calculation is clear. So that is how you find. So anytime you have a radioactive process, you always employ the Einstein's energy equation. You always use the Einstein's energy equation. So I'm going to move on to the next question because of our time. I'm going to be moving on to the next question. If you have any problem, always indicate so that I can, make further clarification. That was just question number 3. So let's go to question number 4 now. So question number 4 says that we have this circuit. So I'm just going to sketch something that looks like it. So we have this circuit. It goes like that. Then we have it goes in this manner. Okay. So here we have V1, and then this one is 3 ohms, and here we have V2, and then here 6 ampere is going here. We have 2 ohms in this place, and then here we have 6 ohms. Sorry, I'm always struggling to draw ohms. Yeah. Okay, somebody said it's complicated. Sorry. You just have to like process it a little after the other. So let's do this one now. You see, this when you see questions like this, what you need to do is that you need to analyze the parallel connection and the series connection. Now in this place now, how do we know who is parallel? How do we know who is in series? So what you need to do is that you need to go and trace where your current is coming from. Since it's coming from here, you see, as you are going and you get to a junction, when you notice this junction now, you will notice that before current can reach this 2 ohms and 6 ohm resistor, you notice that the current have to split in this place. One has to go like this and one has to go in this direction. Whenever you notice that current needs to split before it gets to individual resistors, That means that these resistors, they are in parallel. They are in what? Parallel. Now let me tell you what is common in parallel connection. Now for parallel connection, voltage is always common. Voltage is common for what? Parallel connection. And what do I mean by that? So what do I mean by this? V is common for parallel connection is that, let's say for example, I connected these guys. I'm just going to be using a line to indicate resistors. So let's say resistor 1, resistor 2, resistor 3, resistor 4. All of these guys are connected in parallel. Let's say they are connected in parallel. And let's say the source that all of them are connected to, let's say the actual source that all of them are connected to is giving me 10 volts. What the meaning of V is common to parallel means is that, you see, each of these resistor, they will be experiencing 10 volts, 10 volts, 10 volts, and 10 volts. That is what we mean by parallel connection. So they will always experience the same voltage for parallel. So what will be different for them like that? That means that current I is different. I will be different. So still for parallel connection. However, reverse is the case. When you get to what? Reverse is the case when you are dealing with series connection. So I believe you get the idea. Reverse is the case. So V is different in a series connection while current is common. So I'm going to be using that to answer this question now. So I've been able to establish that 2 ohms resistor, 6 ohms resistor, both of them are in parallel. Since both of them are in parallel, that implies that the only thing they have in common is voltage. So that means that whatever voltage that is entering here is the same voltage that is also what? Entering this place at this. So they have a common voltage, which only one of them is going to be relevant with. So now, meaning that from this first guy, from this 6 ampere, I can easily use my Ohm's law to get my voltage. So let me call that voltage on the 2 ohms. That will be what? Using IR. And then that will be what? 6 ampere, which have been given in the diagram already, multiplied by what is the resistance? That will be 2. So that means that the total voltage here is what? 12 volts. So what does that tell us? If 12 volt is going into the 2 ohms resistor, 6 ohm resistor down here that is in parallel with this, we also experience the same voltage as well, because they are a parallel connection. So that means that this V in this place too will also be 12 volts. And so we can say that 12 volts, so for the 6 resistor, so 12 equals, what's the current that is going here? We don't know the current that is going inside the 6 ohm resistor, but we know the resistance, which is what? 6. Automatically, what does that imply? That implies that our current going into the 6 ohm resistor will be 12 over 6, which will be 2 ampere. So which will be 2 ampere like that. So I believe that makes sense to us. So now I've been able to get that. So with this now I can get what my V2 is. So my V2, mind me, I think I've made a mistake in representation because V2 was already here. So this one is talking about the V that is going to the 2 ohms. V that is going to the 2 ohms. I did not mean this particular V2 that we are looking for. So okay, so let's go on now. You see, like I've said, the same voltage is going into the 2 of them, but it's not the same current that is going into the 2 of them. Now, what do current always do in a parallel connection? Since current is different, what they do is that, if you notice, 6 ampere is going here, and it will make it to this junction. In this place, like we have been able to find now, 2 ampere is going here. It will also make it to this junction as well. You see, when the 2 of them meet, 2 ampere is coming from down, 6 ampere is coming from up. When the 2 of them meet together, the current will add up. Therefore, the current that will eventually make it to this straight line will be the addition of both of them, which is 8 ampere. So what does that tell us? That means that the current that will enter this 3 ohm resistor will be 8 ampere, and hence we can now measure the V2 like that. So the original V2 which we are looking for, V2 will now be what? The current is what? 8 ampere now, times what? The resistance is 3. So we have 8 times 3 is 24 volts. So we have been able to get V2 like that. That is 24 volts. 24 volts. Now going back to this place now to get our V1. V1 is the total voltage supplied in the entire circuit. As I've told you in this place, you see in parallel connection, from what I taught you here, as 10 volt is supplied here, each of these guys will have 10 volts. It does not mean that, oh, this connection has maybe 10 plus 10 plus 10 plus 10 plus 10 making 40 volts. No, that is not what that means. Basically what it means is that the whole thing here is 10 volts. That's the resulting voltage. So that means that as these two, the first one had 12 volts, the second one also had what? 12 volts. So meaning that all of this place all together, the total voltage across this place will be what? 12 volts. And the voltage we got here was 24 volts. Now these two constitute the entire voltage that is being supplied from here. So V1 will then be 12 volts plus 24 volts, and all together that is going to be 36 volts. All together that's going to be 36 volts. And go to the Telegram channel, you get the question there, and I think somebody sent it on the WhatsApp page as well. So, and that answers the question. That means that the correct answer is option D. V1 is 36 volts and V2 is 24 volts. V1 is 36 volts. I'm taking so much time to explain these things. I hope we are going to be able to finish, hopefully, because this time is really going like. Okay, let's go to question. Please help me direct this person to get the question, because I won't be able to attend to them. The time is running. Okay, the next one says in the nuclear reaction, that's question number 5. Question number 5 says that we have a nuclear reaction. I think we can what's it called? I saw the option earlier. We'll be able to revisit the video. So once I upload it, I will let you know. Okay, so now we have this reaction. We have hydrogen 1 plus lithium 7 then to give 2 molecules of helium 4 2. So don't mind the way the diagram was drawn. Don't mind the way the diagram was drawn. So that's the correct way to put that. So the atomic mass of hydrogen and lithium are given respectively, and that of helium is given like that. So Roman figure 1, energy is released by nuclear fission. Roman figure 2, energy released can be calculated using that formula. And Roman figure 3, the nuclear reaction can lead to what? Chain reaction. The nuclear reaction can lead to chain reaction. So the question is asking us in this place that which of these are correct about the reaction that are represented above. So let's see what happened here in this place. So what we need to do is that we need to find the atomic mass of the reactant and find the atomic mass of the of the product. Once we are able to find the atomic mass of the reactant and the atomic mass of the product, then we will now get the total thing. We'll subtract the reactant from the product and we see what goes on there. So basically how to do that is to multiply the. So we have been given that hydrogen has 1.008 U and lithium has 7.106 U. So that means that total for the reactant will be where is that? That is by nuclear fission. Atomic mass of hydrogen and lithium are 1.008 U and 7 this respectively. Okay, very good. So that will be what? 1.008 U multiplied by how many hydrogen do we have here? Only one of it. Then plus 7.106 U. How many lithium do we have here? Also one. So that means that we add both of these to get for the reactant. So we have 1.008 plus 7.106. So this one gives us 8.114 U. That's total for the reactant. Now let's get the total for the product. In the product side, only one thing is formed, and then that is helium, and two of it are formed here. So we have 2 times. According to the question, what is the atomic mass unit of this guy that was given in that place? We have 7 point, no, for helium is 4.004. For helium is 4.004. So we have 2 times 4.004, and if you multiply this now, so that will be 8.008 U. So let's see what happened in this place now. So we notice that in this place, from this particular reaction, this is a nuclear fusion reaction. A nuclear fusion reaction, because 2 things are coming together to give us 1. 2 things are coming together to give us 1. In fact, all the calculation I just did there, I just did it so that you people can, check what is going on. So that is why I just did it. So you don't need to figure that Roman figure 1, because that Roman figure 1, the nuclear reaction that we were given there is not a fission reaction. It is a fusion reaction. A fission reaction always involves the breakdown of big guys to give smaller guys, while a fusion, that is fusion always bring A plus B to give C, and fission always makes C to split into A and B. So what we know about this reaction now, it is a fusion reaction, and from what we can see here, we can see that the reactant, total for reactant, is greater than total for the product. This implies that energy has been released. Energy has been released because what we started with is more than what we are getting now. That means that energy has been released. Hence, in nuclear fusion, energy is released. Now, so in nuclear fission now, that is not the case we are talking about here. We have so Roman figure 1 should be what? Roman figure 1 is not going to be correct. Reason is because energy is released by nuclear fission. That's what they said. In the reaction we are given, it is not a nuclear fission reaction. So Roman figure 1, we can delete it like that. So let's go to Roman figure 2. Roman figure 2 says that the energy release can be calculated from E equals mc squared, where m is the mass change produced and c is the speed of light respectively. Yes. No, we are not finishing today. Definitely we are going to have more class. We are going to have definitely more classes. Like we will have like close to, with the way I'm looking at it, like 10 classes itself if care is not taken. Anyways, let's see how it goes now. So let me go back to m. So Roman figure 2 is correct. I think I've explained that in an earlier problem that I solved. E equals mc squared can be used to calculate the energy released. I've talked about that before. And Roman figure 3, the nuclear reaction can lead to what? Chain reaction. Which of these is correct? Now, what is nuclear reaction leading to chain reaction? Chain reaction is that it's just like a chain. They are connected to each other. So I will not be able to go into too much details because time is really running fast. But Roman figure 2 is correct, and Roman figure 3 is also correct in that place. So please, I've settled Roman figure 1, that is wrong. Roman figure 2 is correct, but let's look at Roman figure 3 now. Roman figure 3. So Roman figure 3 says that, hello guys, are we together? Very good. So I've cleared Roman figure 1 and I've cleared Roman figure what? Roman figure 2 as well. So the last one I've not cleared is Roman figure 3. You see, chain reaction. Okay, let me just write it here. This one leads to chain reaction. This one leads to chain reaction, while this one does not. This one does not lead to chain reaction. So the only thing that is correct there is Roman figure 2. Roman figure 2. So that means that in that option A to D, none of the option is correct. None of the option is correct. Yeah. So only Roman figure 2 is correct in that place. So take note of that. That means that that has no answer to it. Only because only Roman figure 2 is correct there. Take note of that. Quickly, let me move to number 6. Number 6. Okay, this one is very, very simple. It's just like what we have been doing so far. So let's find that. For cobalt, we have that's question number 6. We have cobalt, which is 5927. So they've given us that the atomic mass unit is 58.9332 U. Now they now want us to find also for a proton, atomic mass unit of proton is 1.0078 U, and then for a neutron is 1.00783 U. So unified atomic mass unit is, that is, U is 931 MeV, which is the same thing as 1.6 times 10 raised to power minus 19 joules. So I will explain what all of these things mean. Now, what they want us to calculate here is what? We want to calculate the binding energy. The binding energy. So to find the binding energy, what we need to do is that we need to find the atomic mass unit, which is the bonding unit of the proton and the neutron that forms this cobalt. So in this place now, we have somewhat like the original that has already been given. So we now want to, I think you'll be able to go over the video again. So now, this is what you need to do now. The first thing you need to do when you see a question like this is that you will have to get the number of protons. So how many protons do we have here? We know that proton number is always down here. That's what? 27. And how many neutrons do we have here? That will be 59 minus 27. So 59 minus 27, what will that give us? That will be 32. Now since we have this now, we will now have that the atomic mass unit of this thing of cobalt that we will need to calculate, not the one that is given now, the one that we need to calculate will now be the number of proton, which is 27, times the atomic mass unit of a proton plus how many neutron do we have here? 32. What's the atomic mass unit of a neutron? 1.00783. So when we do all of this together and we calculate it, we will have 27 times 1.0078 plus 32 times 1.00783. So what will this give us all together? That is 59.46116. Now, so as we have gotten this 59.16116 now, so what we need to do now to find the binding energy is that we need to find the difference in mass. We need to find the difference in mass. That is, we subtract the original mass from the new mass that we have gotten now. So the difference in mass, so just like I did earlier, it's always change in mass that we always find. So the change in mass will now be 59.46116 minus what is the original one that we had earlier, 58.9332. So when you subtract these two, okay, you're saying that something is constant. Is that a question? Please let me know if that's a question so that you can ask properly. Oh, the U is like a unit. It's called it's called the atomic mass unit. Atomic mass unit. So yeah, I will explain that when I get there. Yes, I will explain it when I get there. So the change in mass, according to what we have here, the change in mass is 0.52796. So that's the change in mass. That was given in the question. How do I get the 58.932? That was given in the question. That's the original that was given. Okay, thank you for helping me give you that response. So now that we have gotten the change in mass now, so we need to convert. So that U has been given as what? U equals 931 mega electron volt. Now electron volt, whenever you are dealing with all these quantum physics and the likes, so energy is always measured in electron volt. Energy is always measured in electron volt. Are you following me? So since energy is measured in electron volt, then please let me know if we are together. Let me know if we are together. Okay, very good. Thank God we are together. Okay, so now this U now we need to convert it now. We need to convert it to joules. And what's the first process? We will use the fact that U has been given as what? 931 MeV. 931 MeV. So instead of writing U here, this thing will change to 0.52796 multiplied by our U is 931 MeV. So that would be, so let's multiply that. What do we have? We have so this times 931, that will give us 491 MeV. Now in this place as well, 1 EV is given as 1.6. It was given in the question already, so if you look at that very well, 1.6 times 10 raised to power minus 19 joules. So okay, thank you very much. Those of you that are helping me respond to those who have issue, thank you very much. So this one we got 491. Let me put the decimal point. That will be 491.53. 491.53 MeV, like that. And then what is this guy? Mega. What is mega? So 1 electron volt is this guy. So 1 electron volt is 1.6 times 10 raised to power minus. Can the sound be muted? Okay, I don't understand. Like, is there a background sound that is disturbing? Or which sound are you referring to, please? Oh, sorry, it's actually raining here. I think the sound is coming from the rain, and I've closed all my windows, but the rain is very heavy. So sorry about that. But are you able to hear my voice at all? because it's the rain. So I'm sorry, I don't have control over the rain. So that's where the background sound is coming from. Okay, so let's proceed. Okay, let's proceed. So we have this now. Now, this is just a game of conversion. And if we all got it up to this place, what I'm to do next is not any big deal at all. So this is equal to 491.53. Now this thing is just showing mega, 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 mega. So you know how we used to have megabyte, kilobyte, all of those things. So mega has a power of 10 raised to power 6. Mega has a power of 10 raised to power 6. So instead of writing capital letter M now, I will just say this thing is times 10 raised to power 6 times, so I'm left with electron volt. This EV is known as electron volt. Electron volt. So I will advise you to read more about this. Go and carry your new school physics and go to those last parts, all those energy quantization parts. Go and check it. You see more of this, how this electron volt and everything work. So this one electron volt is here, 1.6 times. What is KB, so you can know it? Do you mean? And but the rain is going down small. Okay, I mean KB, kilobyte. I'm just using kilobyte, megabyte. Like, you know, I'm using that because you can relate with data that you buy. So let's use kilogram, megagram, which is not like that common, and all of those things. Okay, yeah, I like this person. School something. Thank you for the please. I think this person is doing a good job clarifying any of those things that people are. So thank you very much, school. I like that. So now let's continue. So in this place, what we have here is that so 1 electron volt has been given as 1.6 times 10 raised to the power minus 19 joules. So we were done with the original work since now all we are doing is conversion. So first of all, we multiply that, all of these things together, times 1.6. That will give us, when you multiply this and this 1.6, you have 786.45. Then that will now be times, so what you notice is that this 10 part, this 10 using indices, the power will now be 6 minus 19, which will be 10 raised to power what? Minus 13 joules. So to convert to standard form now, you take this thing back twice. That will be approximately 7.86 times 10 raised to power. Since you are taking it back twice, that will make this power to go to what? 2 minus 3 like that, which is what? Minus 11 joules. So the correct answer in that place is 7.86 times 10 raised to power minus 11 joules, and that's the correct answer. We are really spending so much time on these questions. Please, let's try to be a little bit faster. Okay, this one says if light with photon energy, and the reason why I put this set of questions as my first questions is that most people are not always getting to this part of their syllabus. So the people always cover the common part, but you see these parts, they are very hidden, and most students always struggle with it. So yeah, this is the correct answer. Thank you for that. So let's go forward. Number 7, if light with photon energy 2 electron volts is incident suitably on the surface of a metal, and the surface of a metal has work function 3 electron volts. So quickly, let me explain that. You see, the concept of number 7 now, what this thing is explaining here is what we call photoelectric effect. And what is photoelectric effect? Photoelectric effect is simply this is what happens. Light will come and be incident. Light will come and be incident on the surface of the metal. Now, if this light has enough energy, so what will happen is that electrons will now begin to go off from the surface of the metal. That is what we call photoelectric effect. Hey, please don't take us back. Oh, don't take us back, please. I subtracted. You see, the please, if you were paying attention, please let me explain to these people. You will get the actual atomic mass unit was given, which is this in the box. You can see that. Then you will now use the atomic mass of proton and atomic mass of neutron that has been given, knowing that cobalt has 27 protons and 32 neutrons. So since you have 32 of neutrons, you multiply it by this atomic mass unit. Proton has this, you multiply it by 27. So when you get the two together, you will add them. So that will give you the new mass of cobalt when the binding actually took place. So when you get that, you got 59.46116. So to get the change in mass, you subtract the previous from the final. So the bigger one minus the smaller one. That's how I got my 0.52796. So please, let's pay attention. Going back to number 7, please. Photoelectric effect is the effect of what? Electron leaving the surface of a metal due to what? Due to light being incident upon that metal. Due to light being incident upon that metal surface. That is what photoelectric effect, that is what it deals with. Now, this is now what happens. You see, every metal, they have what we call work function. Every metal have what we call work function. And what is work function? Work function is just that thing you need to first of all overcome. It's like you want to collect money from somebody and the person is holding on to that money tightly. So before you can collect the money from them, let's say they are only holding a bundle of, let's say, 5,000 naira. As this person is holding on to that 5,000 naira now, you need to drag the money with them. In the process, you ended up tearing two of the notes. You know, you want to drag 5,000 naira, then you ended up tearing 2,000 naira notes. When they see that, this money is already tearing, and they decide to what? Let it go for you. So at the end of the day, you have what? 3,000 naira. Now, so that is exactly, that 2,000 naira is like the work function, in the sense that this light that is incident on the metal surface, it must first of all cause the electron to vibrate. They will now vibrate at a threshold frequency. So the work function W is given by the formula HF naught. What is H and what is F naught? H is the Planck's constant. So you need to go and read that last part of your new school physics to get this thing very well. This is the threshold frequency. Electron will vibrate on the surface of metal when light is incident on it without the electron jumping out. So the threshold frequency is just sufficient to prepare the electron for motion, but the electron will not jump out at that moment. So when that has happened, if the energy that the light is bringing, if the energy is enough, is compact enough, that means that after, let's say this thing is carrying an energy of 5 eV, then the work function of this guy is, let's say, 2 eV, like I've described. So after these 5 eV, I've already used 2 eV to overcome the electron so that they can have threshold frequency, and the work then will be called the work function. What will be left is 3 electron volts, and that is what this electron will convert into kinetic energy, which is also called stopping potential. So they will now convert to kinetic energy. So what does that tell you now? Energy of the light that is coming is equal to the addition of the work function plus kinetic energy that they will gain, that the kinetic energy that they will gain. So let's now go and look at the question now. So I'm going to be the one asking you that question now. So you tell me, Now, the light that is coming has energy of 2 electron volts. Please pay attention. You answer that question. Now, it has 2 electron volts. Then this metal itself has a work function of 3 electron volts. So they want to ask us what is true here. A says no electron will be emitted. B says few electron emitted will have a maximum kinetic energy of 3 eV. C says many electrons will be emitted. D says the few electrons emitted will have a kinetic energy of 1 eV. So what do you think will happen here? The light that is coming has 2 eV. Metal itself has a work function of 3 eV. So what do you think will happen to the electron? So let me hear your feedback. Oh, somebody is complaining about network. Okay, very correct, very correct. That's very, very correct. Yeah. So it seems it's only school that is following me in this whole class. Oh, I hope the rest are with me as well. Very good, very good, very good, very good. No electron will be emitted. No electron will be emitted. Very good, because the energy of the light that is incident is not even enough to overcome the work function. So yeah, good one. I like the fact that you people are following. Good one. So let's move to the next question. The next question says, an electron is accelerated from rest through a potential difference of 70 kilovolts in a vacuum. Calculate the maximum speed required by the electron. So given this, okay, so it's quite similar. In this case now we have potential. So you know that work done by a charge, if you remember your electricity and everything very well, is QV, where Q is the charge and V is the what? Potential difference. So in the case of this guy now that we are dealing with, here, is accelerated through a potential of that. Calculate the maximum speed required. So all of this QV will now be converted to kinetic energy. So this is a case of conservation of energy. You know, energy cannot be created nor destroyed, but they can be, you know, changed from one form to another. So all the QV will now change to what? Kinetic energy. Don't forget, one is the velocity there, which is the small v. So you have been given Q in the question. Q is the charge that you are given in that place. That is 1.6 times 10 raised to the power minus 16. And you have been given the mass. Mass is 9.1 times 10 raised to the power that 31 that you are given. So that can be 31. That will be minus 31. Please take note. Electron is not big. Electron is a small guy. So mass of electron is 9. Please correct that in your book. That will be 9.1 times 10 raised to the power minus 31 kilogram. Minus 31 kilogram. Then followed by what else were you given there? The potential difference, 70 kilovolts, like that. So what you just need to do is that what? You make this one your sort of formula. So let's see that. Cross multiply. What do we have? We have 2QV, capital letter V now, equals mv squared. That means that v squared equals